Okay, so we've done a couple of work problems. Work is a classic integral problem because it is the product of two things, one of which may be changing um, as the other one changes. So calculus gives us the tools to solve those. Another example is fluid pressure. Okay, so fluid pressure is defined as the weight density times the height. So this has to do with like when you're building a dam on a river or something like that. The pressure that is against the wall of the dam depends purely on the stuff that it's damming up, which for us is typically water, um, times how deep that water happens to be. Okay, so at the very top of the dam where the water is splashing against there, doesn't have to be particularly strong, but as the water increases in depth, the force increases, so dams are generally wider at the bottom so they can support that. Okay. A couple of other things. So fluid pressure is force per unit area. Weight density is a weight per unit volume. We saw that with the weight of the olive oil as well. There are lots of different things that we could know the weight density of, but certainly that has an effect on this. But because this fluid pressure is defined as a product, then if the heights were changing, for example, then we would be able to use calculus to help us calculate an overall fluid pressure. All right, so this is also story time. Some people got the benefit of this story already, but this is about the Great Molasses Flood of 1919. It says at 1 p.m. on January 15th of 1919, a 90-foot high, 90-foot diameter cylindrical tank in which the Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston's North End exploded. Molasses flooded the streets 30 feet deep, trapping pedestrians and horses, knocking down buildings, and oozing into homes. It was eventually tracked all over town, even made its way into the suburbs via trolley cars and people's shoes. It took weeks to clean up. There's a picture in your book on page 421 if you want to see some visual record of the Great Molasses Flood of 1919. So what we've got here is our tank, which is 90 feet wide and 90 feet tall. This is a large tank. Okay. And it is, given that the tank was full of molasses, that has a weight density of 100 pounds per cubic foot. What was the total force exerted by the molasses on the bottom of the tank at the time that it erupted? Okay, so we want total force exerted on the very bottom part. Okay, well this is going to be, if we look at this, this is force per unit area for the fluid pressure, which is going to be the weight density times the height, which will give us units again, in this case, of pounds per square foot. And then if we multiply by the square feet that occupy the bottom of this tank, we should get something in pounds, which is how we measure force. So not a lot of calculus going on in this part, but our fluid pressure at the bottom was the weight density of 100 times the height, okay, which is going to be 9,000 pounds per square foot. And so if we want the total force on the bottom, which is going to be measured in pounds, then we're going to do that 9,000 and multiply by the area on the bottom. So this has a radius of 45 feet, and so an area of pi times 45 squared. This will have units of square feet, This had units from above of pounds per square foot. Square feet cancel. This will have units of pounds, and that works out to, are you ready? 57,225,526 pounds of force on the bottom of this tank. All right, now let's take a look at the calculus part of it. Okay, so part B here, what was the total force against the bottom foot-wide band of the tank wall? So if we came up just 1 foot here and traced around here, assuming this tank, I don't know if it was made of steel or if it was made of wood slats like a giant barrel, but at any rate we have a 1 foot wide strip on the bottom, so that's going to be a foot tall. We know here that the fluid pressure is going to be, if we were to take a sample slice, and we'll pretend this green one that I drew in there was the sample slice, okay, then it is at a depth here of, we'll call that maybe D for the depth. See what direction we want to go with this problem. And at that point, what we've got for an area, we've got a little strip that comes around in here, and its area has a little bit of thickness. We'll just we'll change the D to a Y so I don't have to write DD. So we'll say that it is Y feet down here from the top to where I drew my strip. And this is going to be a thickness, again, of dy. So this little sample strip, which is not a foot wide, it's only dy wide at this point, and it's going to be 2 times pi times 45 long. So we have a consistent area of these strips of 90 pi times dy. This is going to have units of square feet. We have the weight density times the height, so our pressure in this case, our little bit of fluid pressure is going to be the weight density, which was 100 pounds per cubic foot, okay, times the height. The depth here is y, so pounds per cubic foot times feet. This has units of pounds per square foot, and if we multiply that by our 90 pi dy, which has units of square feet, the square foot units will cancel. This will have units of pounds. So, what that B was that I had in there. Let's extend our page here. Now we just want to add up all of those sample slices. Okay, so let's clean this up a little bit. Our little bit of pressure was that, but now we have changed it into a little bit of force once we've done this. And so we have 9,000 pi y dy, and we are going to do an antiderivative there. The way I defined my y, it looks like I want my y's, if the top of the tank was 0, then I'm going from 89 to 90. On that. So obviously that's a 4,500 pi y squared evaluated from 89 to 90, and that works out to be just on that bottom part, 2,530,553 pounds of force exerted just on the bottom 1 foot wide rim of that tank. Okay, that's a lot of pounds. Big numbers again. Hopefully you noticed an intense reliance on keeping track of units and making sure that the units that we put together ended up giving us the units that we wanted at the end. Okay. So changing labels and things on the way to help us keep track of that, drawing and labeling the picture so that we knew if we said that that was Y units down, Y feet down from the top of the tank, that we knew what to put as our limits here based on how we drew the picture. Okay, you can draw this picture and label and start things in different places and potentially get a different setup that should end up with the same answer. So it's important to have that picture and the setup and the work along the way so somebody can follow what it is that you did. All right, so there is our fluid force via the Great Molasses Flood of 1919.